So far, we discussed several designs aimed at increasing the open circuit voltage of the crystalline silicon solar cell. In this video, we will focus on another important external parameter, the fill factor. First, we will briefly discuss the ideal fill factor of a solar cell. Then we will demonstrate that the fill factor of the cell is most influenced by parasitic resistance. We will then turn our focus to the front contact production process. The fill factor is calculated from a JV curve measurement as the ratio between the product of the maximum power point voltage and current density divided by the product of the open circuit voltage and the short circuit current density. This is shown in this slide as the ratio between the dark blue square and the pale blue square, as was demonstrated before. For an ideal diode, an empirical relationship between the cell's open circuit voltage and the fill factor has been found, where the VOC in lowercase letters is defined as the actual VOC normalized to the thermal voltage Kb times T over Q. The normalized VOC includes also the previously mentioned ideality factor that links the dominant recombination mechanisms in the cell. For an ideal solar cell, this ideality factor is taken to be 1. This empirical relation represents the maximum obtainable fill factor at a certain open circuit voltage. However, in practice, this value is lower by parasitic resistances. In order to explain the effect of the parasitic resistances, we consider the one diode equivalent circuit of a solar cell with JPH, the photo current generated in the device, JD, the diode current in the parallel diode, and RS and RP, the series and shunt resistance, respectively. The JV characteristics for the single diode model, taking into account the series and shunt resistances, is given by this expression. When the shunt resistance RP is decreased, the fill factor of this cell will decrease by having a steeper slope at the intercept with the current density axis. A decreased shunt resistance may, for instance, be due to ineffective edge isolation. In the video on the doping of crystalline silicon wafers, we have discussed methods to increase the shunt resistance of the cells by edge isolation. When the series resistance of the cell is increased, the fill factor will also decrease, but this time the slope at the intercept with the voltage axis will be reduced. An increased series resistance often results from a too high resistance of the metal top contact. We will now discuss the front metallization of the standard silicon solar cell, as this part contributes most to the series resistance. In addition, we will focus on the production process and design consideration to maximize the fill factor of the cell. In a standard crystalline silicon solar cell, the current flow inside the wafer is perpendicular to the surface. The p-type base contributes to the total resistance with R base. Once the current reaches the emitter layer, it will follow the lowest resistance paths towards a metal contact, as indicated by the arrows. Note that in reality, some of the current will flow directly from the emitter into the nearest metal contact. Most of the current will be collected by thin and close-spaced metal contacts that are called fingers. Wider contacts, called the bus bars, will further conduct the current into an external circuit, or in case the cell is connected in series, to other cells, and it will transport the current to the next cell. The pattern of the metallic front contacts are most commonly produced with a screen printing process. A metal, in this case silver, is applied as a paste. This way, it can be transferred through a frame with any desired pattern by spreading the paste with a squeegee. Silver paste is printed on every gap in the pattern frame. The overall process is comparable to, for instance, t-shirt printing. A fluid paste is swept across the mesh and leaves a pattern on the substrate. After applying the paste, the contacts are fired in the furnace at approximately 800 degrees Celsius. This way, the silver will burn through the silicon nitride passivation layer, which was introduced in the previous video, and it will make contact with the emitter layer. To summarize this video, we have discussed an empirical relation between the open circuit voltage and the maximum obtainable fill factor, but that in reality the fill factor is mostly affected by parasitic resistance. The front contacts of the cell contribute to the series resistance. Bus bars and fingers are applied in a pattern by screen printing.